We like LEDs because they are very efficient. And in illumination, almost all incandescent bulbs have been replaced by LEDs because of their efficiency. For every watt of electrical power that I feed in, I get almost a full watt of optical power out. Their efficiency is high in terms of what's in, what's out. But also in terms of quantum efficiency. Almost for every hole and electron that recombine in the electrical part of the LED, we get a photon out. 100% efficiency, close to. But is the efficiency as we experience it for illumination the same as the efficiency that we see for communication? So maybe also say that if we illuminate the LED up to a certain level, and then if I add one more whole electron pair that we recombine, do we get one photon difference out in terms of a modulation of that signal? And the answer is no, they're not the same. So I would like to discuss about something which we call differential quantum efficiency for modulation, when we make minor changes to the signal and then we see whether that also gives minor changes of the modulation of the electrical light that comes out. And in order to study that in more detail, I would like to go into the details of the recombination of holes and electrons in the quantum well of an LED. How fast does that occur? At what rate does it occur? And at what efficiency does it occur? Now, let's study that in more detail. And let's call the number of holes and electrons in the quantum well n. The number of electrons, but also the number of holes are n. And then the change of the whole electron pairs is of course proportional to the current that we feed in. Almost for every electron, we create an electron hole pair in the quantum well. So we divide the current I divided by Q to get the number of electrons that come in. But talking about the change of that number, there are also whole electrons pairs that vanish, that recombine, so to say. And then there are three effects that we need to discuss. One is the effect that we like. That's the radiative recombination. That's the B term in the ABC equation. So the number of recombinations is B times n squared. You need a hole, you need an electron. The chances that they find each other is n squared. So B times n squared is the radiative recombination rate. But then there are two terms which are non-radiative. One is the Shockley-Reed-Hall recombination rate. That's quite often related to defect states and impurities in the LED, and that's proportional to n. So A times n, B times n squared. Then there is a third term, the Auger recombination, sometimes also called the droop. And that particularly kicks in when the currents are high and when the concentrations are also very high. So it's C times n cube. These three terms describe the number of recombinations. But out of these three terms, only one term is relevant for the generation of photons. So there's only one term that contributes. And therefore the efficiency, the quantum efficiency that we like to talk about, is the ratio of that. So it's B times n squared divided by the whole ABC equation, A times n plus B times n squared plus C times n cube. And that ratio is the quantum efficiency. But I like to move on. I like to talk about small variations of that signal. In order to do that, I split the total signal, I of t, the current that comes in a DC part and an AC part, the modulation part. The DC part, I give an index DC and I write it with a Roman font. The small signal, I write in small symbols, small I of t. Similarly, of course, I can do the same with the carrier concentrations, with the number of holes and electrons. N, capital N, consists of a DC part in Roman and DC, plus the small signal, small n as a function of time. So these combined signals we can put into the expressions for the rate recombination. Let's do that. So then the change of n, the change of number of electrons caused by the current, the ndt, is proportional to the current divided by q, minus everything that comes in as recombination. And there I need to express that whole term, n plus small n, capital N dCn, plus small n, squared, and taken to the third power, fed into the ABC equation, and that gives me a plus 2bn plus 3cn squared times nt. It is more or less the same as taking the derivative of that polynomial and then take a first order Taylor expansions for small variations, small n of t. And now for this expression, I can also find the differential quantum efficiency for small signal modulation. And of course, as you see from the equation above, the 2bn part is the effective part, the radiative recombination, the one that we like for the photons that come out for modulation, divided by the total number of recombinations, and that's a plus 2bn plus 3n squared. And if you compare that with the previous expression for the quantum efficiency for illumination, for the DC part, it's a different expression. And if we combine that, we see different curves. And the optimum, the most efficient operation point for illumination, is a different point as the optimum operational point for communication. And if we drive the LED further at higher and higher currents, we see that somewhat the droop reduces the efficiency for illumination, but the efficiency for communication goes down even faster. Now, is it important to talk about the efficiency of the LEDs? Or, if we talk about communication, should we talk about the bandwidth? Well, you may remember Shannon-like equations where you say that the throughput is proportional to the bandwidth and proportional to the signal-to-noise ratio, but then the logarithm of that signal-to-noise ratio. And then you rather boost the bandwidth, because boosting the signal-to-noise ratio only gives you a little bit of throughput extra. But for LEDs and lasers and optical communication, that's not really the true story. That's not the full story. If we have a stronger signal-to-noise ratio, we can still modulate at higher frequencies. And because we have a stronger signal that is more efficient, we can just repair that. It gives a little bit more noise if we compensate for the frequency response, but we can afford it because we have a stronger signal. And if we do the math here in full, it turns out that bandwidth and signal-to-noise ratio are equally important. So we should not only go for bandwidth. Having said that, I would still like to talk somewhat about the bandwidth, the frequency response of the LED, and the previous expression, the ABC expression, which we have been writing in terms of small signals as a function of time, we can rewrite as a function of frequency. The derivative of n now becomes j omega, n of omega, is equal to the spectrum of the current, I of omega, divided by q, minus the recombination, a plus 2bn plus 3cn squared, multiplied by n omega, the variations in whole electron pairs as a function of frequency. So I can calculate the response there. And if I do that, basically n of omega divided by I of omega, I get an expression that is 1 over j omega plus a constant. Constant a plus 2bn plus 3cn squared. But that's a low-pass frequency response. That's a low-pass filter. And the turnover frequency happens when j omega is equal to a plus 2bn plus 3cn squared. And then we see that if we increase n, if we increase the current, the 3 dB bandwidth of the LED goes up. Yes, stronger currents give a higher bandwidth. We like micro LEDs, they have a higher bandwidth. But their efficiency goes down. So it's an interesting debate about where to find that optimum. And that's not always by going for higher and higher current densities. At some point in time, you may just also like to benefit from a stronger signal-to-noise ratio. Have a system that is highly efficient, that generates a lot of photons, a lot of modulated photons for the current that you feed in. All in all, if you'd like to know more, I like to refer you to our papers, in particular the IEEE 2022 paper, where we described the throughput optimization for infrared LEDs, where we are playing with these effects, exactly these effects, and where we introduce concepts like differential quantum efficiency for modulation. And we show that that is different from quantum efficiency for illumination. So next time, when you calculate signal-to-noise ratios and bandwidth for LED, it may be interesting to have also a look in these papers.